Okay, so thank you. Let me restart our session again because it's a time at the 5:15. And yeah, at the first, my deep apologies for confusing the speakers and also the audiences. And yeah, it's a really bit unfortunate accident. So anyway, I would like to start the session on application and the industry. And I would like to welcome all the speakers and also the audiences offline and online. And my name is Ryosuke Shibasaki. Actually, I'm a professor of the University of Tokyo, Japan. And yeah, anyway, today we are supposed to have 5 speakers. And the first speaker would be Mr. Narayan, and the first speaker is available.
I hope you can see my slides. If not, please let me know, yes? Okay, first I'd like to introduce myself, and I have to apologize, my voice is not clear today. I'm having cold since last couple of days, and it's still clear. I hope you can understand my voice in any case. Okay, my name is Narayan Tal, and I'm working as a lead of satellite application and GNSS working group at Nepal Astronomical Society, which is located at Kathmandu, Nepal. And today I would like to present on the topic GNSS for avionics and CNS ATM, which is the communication, navigation, and air traffic management domain in air navigation services or in aviation. And within our working group at NASA, we have several students who are working as system engineers from different universities in Nepal. And I have listed the names of all the system engineers who are working in our project here. So at Nepal Astronomical Society, we have our motivations to facilitate the use of GNSS in different applications and to promote science and technology through it, and also to support the socio-economic development in Nepal. And for that, we have different agendas in our working group. The foremost is to transfer the technology and know-how in GNSS domain. As you already know that Nepal is one of the developing countries, and we do not have established space program as well as the GNSS program. A few universities, they have started the GNSS programs since last few years, but in the application side, it is still in very infant stage. That is why we want to utilize our platform at NASA and bring students and researchers from different universities to conduct research projects with an application point of view in mind. And our main application sites are in space transportation, aircraft operation, drone operations, and on the other side, the spillovers in health, agriculture, education, and other sustainable development goals that are defined by the United Nations. And we have drafted short-term, mid-term, and long-term goals, how we have to achieve these objectives and targets. And we are also fostering our regional and international cooperations for the applications and use of GNSS in multiple domains. In this table, you can see we have summarized in short text our short-term, mid-term, and long-term goals. And at the moment, we are focused on our short-term goals, which is in GNSS applications to use the GNSS technology in aviation domain in particular. And for that, we have started 2 projects highlighted here, which is the satellite navigation for avionics and CNS ATM. And at the same time, we are also conducting a project which is related to the Dream Chaser orbital mission, which is a reusable space vehicle. And the idea there is to do a feasibility analysis to land such a space vehicle in an airport in Nepal. And for these projects, we have started with conceptual know-how to understand the concept of operations. And in the next phase, we will also acquire GNSS hardware to do some research, research activities with different researchers and students from Nepal. At the moment, because of COVID and all the researchers and students are working or studying from home, we are doing weekly project meeting for 3 or 4 hours. And we also do weekly analysis of the different concepts that we discussed, mostly in the application-oriented side. And we are using a system engineering framework to conduct our projects. So I will start with the first topic, which is satellite navigation for avionics and CNS ATM. Yeah, in this slide, you can see in the right side the complete overview of how different navigation systems can be used in airspace, or let's say air navigation services. It could be either the civilian air navigation or military or even the space vehicle. As you can see here, sorry. Here, this is Dream Chaser re-entry, which is analogous to the space shuttle that we had like in 10 years ago, which was ended in 2011. But there are other reusable launch and reusable vehicles that we entered to the atmosphere, and we could also support those vehicles during the guidance, navigation, and control through the use of satellite navigation. And in this architecture, you can see conventional navigation aids, for example, DME, and this LDAGs, and other navigation technologies that support the in-route navigation, approach, and landing of the aircraft. And here is the well-established ILS, which is called Instrument Landing Systems, that guide the aircraft for precision approach and landing, even in the zero visibility condition. The idea here is to explore the satellite navigation because it is the key of the avionics and CNS ATM systems, according to the International Civil Aviation Organization, which is acronymed as ICAO, the specialized body of the United Nations, and which is the oversight authority to implement the standards and regulations for civil aviation throughout the world. And in this context, the GNSS is a key technology in the performance-based navigation, which has to be adapted in each of the ICAO contracting state. And here we are looking in a generic view, but our focus is in the PBN plan of Nepal. And so we have analyzed the PBN plan of Nepal and also found out the status quo, what is the current status and what is the next 10 years status, and what Civil Aviation Authority of Nepal is planning to implement. And we have found out that there is a big lack of GNSS know-how and expertise in the Civil Aviation Authority of Nepal or in the aviation industry in Nepal. Therefore, our goal is to familiarize the GNSS concept and also the GNSS integrity concept in cooperation with the university in Nepal, and to guide students to conduct projects related to GNSS integrity or aeronautical integrity, so that they can go to the aviation industry and apply their knowledge in the future. And here is one particular example of what we could do in the future, or what the Civil Aviation Authority of Nepal or aviation industry in Nepal could do in the future. Here I have shown in the slide the S-bus performance, which is the space-based augmentation system. I'm pretty much sure that all the audience and guests here are well known to this technology, the space-based augmentation system. And Nepal, even though it doesn't have its own satellite navigation or satellite augmented system, we can of course utilize the existing system from India or neighboring country who provides the augmented the information through Gagan. And here, this is an example of Nepalese airspace, how the performance would look like if we use the S-bus for aircraft operation. And there are two types of services currently supported by S-bus, which is RNP 0.1 and APP1 services. And these are the requirements derived from ICAO standards. And in the left side, I have plotted for 1 day, it is from 9th of February. And here in the top figure, we have horizontal protection level and horizontal protection error. In the bottom, we have vertical protection level and vertical positioning error. And this is just one sample, and our target is to teach or to guide all the students how to conduct this kind of analysis and what does it mean to have a varying protection level in horizontal and vertical dimension, and how it correlates to the requirements specified by ICAO in the frame of aircraft operations and navigation. As you can see here in the horizontal protection level, the protection level shown by the green curve, it is varying from midnight to the next day in the 24-hour timeline. Of course, we have more how do you say protection bound in the middle of the day. This is in the UTC time, so Nepal time is shifted by around almost 5 hours. So you can see it's around in the 6 a.m. in the morning, which is equivalent to midday in Nepal. So it's a bit inflated. It could be because of dilution operation or even for the ionospheric activities, because it is more pronounced in the afternoon. And you can see in the y-axis, it's probably not clearly visible, but it is well below 30 or 40 meter. And if you check here the requirements for two services, the horizontal accuracy is 72 meter, and for RNP 0.1, which means required navigation performance 0.1 nautical mile, and for FPP1 it is horizontal 60 meter, and the alert limit, which is the utmost error level, which shall be always monitored. And if the protection level is above or the positioning error is above this alert limit, the aircraft cannot use these services for aircraft navigation. And similarly, in the bottom figure, we have similar plot for vertical protection level and vertical positioning error. Positioning error is shown by the blue dots here, which is here within the 1 or 2 meter range. But the protection level, it is a safety bound and which is inflated. And it goes up to here, in this case, around 75 or something like that is. So this is only an example of one day. Our target is to do a robust analysis for larger data set and to characterize the performance of Gagan system in Nepalese airspace, particularly in Kathmandu, and we will also try to see if we can do similar analysis in other regions of Nepal. So in the next slide, it shows the Stanford plot, which is highly used in the aeronautical integrity. This gives us an overview whether the system, the SPA system, is available for different categories of approach and landing or not. In the y-axis, we have the vertical protection level, like the one I showed in the previous slide, and in the x-axis, we have the vertical positioning error. So in this 2D diagram, we can correlate the error to the protection level and see if the system is available or not. Here, the system is unavailable means the positioning error is higher than the protection level. So in this case, the system cannot be used. It should always be within the vertical protection level. And if the vertical protection level is way above the alert limit, as we saw in the previous slide, then it would give us misleading event. And in the case of positioning error, which is way above the alert limit, then it would give us hazardously misleading event. This means that it cannot be used. And if we use the positioning which is above the alert level, it would be a hazardous situation, reflecting that it could cause an accident. And in the right, this is a very generic or high level formulations to compute the vertical protection level for SPAS, which can be computed using the satellite geometry given by the ESP square and the variance of the error model, which is computed using the individual variance of each model term, like this fast and long-term correction. This is coming from the fMRIs, satellite clock and orbit. Then we have the ionospheric error. Then we have the aircraft multipath and other noise errors, and then we have tropospheric error. These errors are independent and zero mean in the distribution, so they can be modeled as a summation of each individual term. Okay, so this is for our vertical one, and the similar Stanford plot can be computed for the horizontal one as well. And in this case, you can see that the system is available all the time. There is no epochs where the position error was above the horizontal protection level. In the previous case, there were few epochs above the vertical protection level. The positioning error was above it, and it was shown here with this epoch here. Okay, so I would like to hand over the presentation to one of our colleagues who is working in the project, Sriju Banjare. She will describe.
Thank you, sir. I hope I'm audible.
Yes, I can hear you.
Okay, so I would like to continue, and I'd like to talk about our project, our mission. The primary mission of our project is to analyze and study the feasibility of landing a space plane, specifically Dream Chaser, in the Nepalese airport. The Dream Chaser orbital mission offers an opportunity with collaboration between Sierra Nevada Corporation and UNOSA to facilitate the promotion of space science and technology. The mission is also providing an opportunity for civilian airports all around the world to land the space plane. Our purpose at NASO is to analyze the detailed outlook on possible challenges that Nepalese airspace would face while landing a Dream Chaser, seek their possible solutions, and ultimately integrate the study to come to a suitable conclusion. The major focus of our study will be to analyze the re-entry of Dream Chaser within the atmosphere and horizontal landing problem of reusable launch vehicles such as Dream Chaser, and to analyze the terminal area energy management constrained within the international criteria for bank angle, angle of attack, flight path angle, and speed. Here in the figure, we can see the concept of operation of reusable vehicle, terminal area energy management, approach and landing. And finally, to allocate the CNS ATM infrastructures according to the international standard requirements. This is it for this slide. Now, I would like to talk about the Global Navigation System satellite in the guidance, navigation, and control of reusable launch vehicle. So the Dream Chaser has the possibility of utilizing Global Navigation Satellite System as a key technology for the guidance, navigation, and control. After the initial descent to the atmosphere, above the ionosphere, the Dream Chaser can be navigated through conventional navigation aids such as tactical air navigation, TACAN, which is equivalent to DME viewer systems. And below the ionosphere, the Global Navigation Satellite System can be used for state vector updates. As we know, the reliability and accuracy of GNSS is way better than other navigation systems. It is also visible in the picture that it reflects the performance of the space shuttle mission. And finally, in the final approach and landing phase of Dream Chaser, we will be using the SBAS GBAST system, the space-based augmentation system, and the ground-based augmentation system based on GNSS for higher reliability and integrity. In the plasma region of ionospheric zone, the use of GNSS is limited due to ionospheric activities. So that is the reason we are using TACAN above the ionosphere. And lastly, even though it is not a part of our project, the GNSS also has precise application for orbit determination and docking as well. Now, thank you. This is from my side. I'd like to hand over to Mr. Narayan Dittal.
Okay, thank you, Sriju, for your explanation of these couple of slides. I would like to continue further on. We have a few more slides. Okay, it's only one slide. And I would like to wrap up this presentation with our analysis and findings so far. Just to remind all of the audience that our project is still ongoing. We have still 3 months left in our project plan. So we have only intermediate results to present in front of you. In the left side, we have a map of Nepal, and here we have integrated.
Excuse me, the presenter, the time is up.
Okay, I was muted. I don't know why. Okay, so in this left figure, in the map of Nepal, different locations are highlighted there. These are the ongoing implementation of ADSP, which is automatic data broadcast system, which is based on GNSS, and this broadcasts the position of the aircraft in a continuous way. So you do not need to have a ground-based system to integrate the aircraft to get the position. And this has an advantage to provide surveillance services where radar coverage is not present. And in the yes, please.
Excuse me, can you hear me?
Yes, I hear you.
Okay, so your time is up now.
Okay, yes, just 10 seconds. I will wrap it up.
ไม่ได้ยินเสียงใช่ครับเพราะเราก็ไม่ได้ยินเสียงทางซูมแล้วถ้าทางเราจะพูดอะค่ะ
Yes, I think I can just wrap up with this slide. As you see, we are focusing to provide better coverage in the northern regions where there are gaps. And yes, our project is find a way to provide the navigation and surveillance services in these two highlighted regions. Yes, I would like to wrap up.
เปิดแล้วค่ะ
Yes, thank you very much. If you have question, please not hesitate.
Okay, I will start now. Hi, everybody. My name is Rainer Horn, Managing Partner of Space Tech Partners, consulting firm based in Europe, but also in Asia. We've been working with MGA for quite some time, and I will give you an overview of what we're doing in GNSS Asia. And also what we have been doing here in the ASEAN region in particular. So I've been a steering team member of MGA for quite some years. My team is largely based in Munich and in Belgium. And we are working with Asia now since over 10 years. In GNSS Asia, we're building industrial bridges and institutional bridges between Europe and Asia, and helping to network also within Asia to drive GNSS adoption, and to really help bringing people together from different domains. We have built a tremendous network of companies across Asia, in North Asia, but also Southeast Asia. And the Southeast Asia focus will come a little bit later. Now, you see here a few examples of past MGA conferences in Thailand, Indonesia, Philippines, Brunei, and also in Phuket once before. So happy to hear that the team is back there. I'd love to join next time round, wherever it may happen. And so that's clearly a great innovation, this conference taking place and also having its side events here and there in Singapore or other places. So today we would like to focus the discussion a little bit on the innovation aspects that we have covered of engaging the youth, engaging young professionals, engaging students and researchers on the topic of GNSS applications. And also how European technology can feed in, because it's largely provided free of charge for the world, the Galileo program and the Copernicus program, how they're being used for integrated space applications. We have recently conducted some hackathons in this regard in the region, in ASEAN, and quite a few trends came out of it, and we heard where the latest innovation and where grassroots innovation is coming from. So these were some of the activities we've done over the last year and a half. We conducted a number of workshops on emergency and maritime applications. We ran hackathons. We had the EU-Japan Week touching on Pan-Asian issues. And we've organized matchmakings between Europe and Asia at the Munich Satellite Navigation Summit, which actually happened just a few days ago, virtually again. The hackathons were a large success. We've done hackathons first physically in India and in Thailand, really showing 120 or 80 people coming together for 2 intense days and shaping up in ad hoc teams or teams that were formed before new ideas. This time round, we had to do it virtually, but we did it way bigger. We covered the whole of ASEAN in cooperation with 3 partners: the ASEAN organization for the Pan-ASEAN contest, the Philippine Space Agency, and last but not least, GISTA for the Thai hackathon. All of them had in common that there was a set of challenges that the teams could tackle, so they could choose emergency, environmental, maritime, or tourism heritage. And I think they came up with quite a number of ideas. So the 200 something people that signed up came from 10 countries. They formed 22 teams, and many of them made into the finish line. And naturally, those countries that had a bespoke contest, Philippines and Thailand, had the highest number of participants. Indonesia, due to the sheer size of the country and population, came in third without a specific contest. So we had high-profile speakers. We had the director generals of space agencies and European ambassadors in the region, but also the Secretary General of ASEAN, speaking about why this activity is important for them. So one of the key focus in this was the sustainability goals, making sure that the ideas ideally are linked somehow to address some of them. Yeah, there's a bit of documentation that we made available to them, both from ASEAN, but also from the European Union side as part of the EU-ASEAN strategic partnership. And these things were taken into considerations by the hackers. I'd like to show you quickly a video. I hope it works and the sound is being portrayed about this event.
This is a Galileo satellite. It constantly sends timing and positioning data back to Earth. And it was the centerpiece of the Galileo Hackathons 2021. Supported by the Association of Southeast Asian Nations, ASEAN, the Philippine Space Agency, PhilSA, and Thai Space Agency, JISTA, the GNSS.Asia team welcomed over 200 hackers from 10 different countries in a virtual ideation competition. In November 2021, innovative and talented individuals from all kinds of backgrounds had the chance to leverage EU space data from the Galileo constellation to tackle global challenges. During the hackathon weekend, over 30 teams gained insights from over 15 presentations from business and space experts, totaling 48 hours of training. What's more, with the help of 25 experienced mentors, the team had to convince 20 jury members from the space industry that they deserved to take home the prize money from a pool of €10,500. 9 teams were the final winners and leveraged Galileo for emergency management, maritime applications, sustainability solutions, and tourism and cultural heritage applications in Southeast Asia, in support of the Sustainable Development Goals. All this was made possible thanks to the collaboration between Europe and ASEAN. This is a Galileo satellite, part of the European GNSS constellation. And with the help of its data, we can create solutions for the future.
So in the next step, we want to dive a bit more in the top trends that we see in the application areas: emergency, maritime, environment, and tourism and heritage. So the solutions that were presented covered these areas. Here, a quick snapshot of what was a top trends and what were top opportunities presented in the area of emergency challenges. Obviously, Southeast Asia has very specific geographic circumstances, and this is what also triggered the ideas, and we saw many ideas coming in this activity. Somebody could possibly go on mute. There's some disturbance here. One example was SIG RISCOS, a distributed mobile participative GIS that was developed and brought forward here in this context. This solution is helping to educate civil defense workers, so helping to mitigate issues when in the case of a disaster or a warning situation. Another example here in the environmental challenges and applications that was INEO. INEO is you having a gaming application that is making a fun way to have citizens participate in environmental issues. So it's a bit of a game, an app game, similar to Pokemon, where people can develop solutions and understand better the environmental challenges. So it's really for social engagement in environmental courses. And this addresses the cases 13 and 15 of the SDGs. When we move over to the maritime situation, addressing SDGs 14 and 9, the areas that are covered are fishing, vessel navigation, and harbor management. An example we would find noteworthy to mention here is Elements Works, a startup that uses state-of-the-art technology for sustainable coastal development. We'll make also the links of these companies available. We've found this quite innovative, as it's being used for fish farms, marinas, and even for bridge operators. Lastly, tourism and cultural heritage applications addressing SDGs 8 and 10 in particular. They aim to support sustainable tourism, the integration of rural areas, and the protection of cultural heritage. So again, here an open source web app that was conceived by the European Commission this time around. So it's a European solution ready for the world, and it's called Cultural Gems. It includes data on selected cultural venues amongst European cities, but we're sure this can also be applied equally for applications in the tourist destinations of Southeast Asia. So lastly, we want to have a deeper dive into the multi-GNSS industry and applications in Europe and in Asia. We have created a repository for you to understand better what is available, to learn more about this. So we would like to invite you to look at the free download opportunities from GNSS Asia and our GNSS Asia innovation blogs. We have market and technology trend reports, already 4 editions. We have recordings of webinars that have been conducted for specific topics on emergency, on maritime applications, and so forth. And of course, specific applications for crisis situations like you see on the bottom right. So the resources are available also on our YouTube channel for easy consumption. That includes several of the lectures done by mentors and the keynote speakers of the past conferences. Also featuring here Thai speakers, Professor Halemron from Thailand, and also based in Thailand, Karen Wang, the head of the UNESCAP space team, who gave a speech on plan of actions on space applications. A number of lectures are available about what is behind Galileo, what is behind Copernicus, special courses on Galileo to know more about it and how you can use it and how you can use it for your innovations. So if you're interested, if you're intrigued, join the community of GNSS Asia in the GNSS Asia Hub. The hub gives you access to networking with Europeans, but also amongst Asian players, and gives you access to all these resources. So you can see the logos at the bottom left, what type of companies are already registered on this. So thank you very much for your time, and thank you for the opportunity to Shiba Sensei, Yoko-san, Kogure-san, and many others behind the scenes. And sorry I can't be with you this time physically at the MGA meeting. Looking forward to the next time. And now I'm happy to answer any questions you may have.
Do you hear me?
Yes, I can hear you.
Unfortunately, I'm not on the stage due to some malfunctions of the microphone systems. So anyway, I am now accessing to a little bit different device. Yeah, okay. Anyway, thank you very much for the very interesting talk. And I have just one question. I understand that the GNSS is a very important component of many systems, but it's just one part. So then, for example, how could we encourage a kind of system integration, including the GNSS component, leading to the, let's say, solution services or much more comprehensive or integrated system development that could directly help or support the users?
Mm-hmm. Yes, I think I can speak predominantly from a European perspective, of course, but I also know that the JAXA team and the Cabinet Office team in Japan and many others are pushing forward in this direction. I think what we can do is making people aware not of the technology, but what you can do with the technology. I think we have to talk to innovators first and foremost. What's the purpose? What's the benefit? What problem do you want to solve? We should not start with the receivers and what the receivers can possibly do. The receivers will find a market when the people discover what can be done. And ultimately, in an age of digitalization, GNSS is a big enabler of digitalization. But ultimately, it's one of many sensors that is used for a smartphone application or for a professional application. So I think the key is to make readily available in simple language what there is and where to find it, but also, as it's done by S-Booster, by our Galileo hackathons and by others, to engage innovators to think about how they could solve geospatial problems. And I think that's the main key here. Okay, looks like the next speaker is getting ready.
Yes, I'm ready.
So thank you. Greetings from Munich to a beautiful Phuket, and hope to see you all next year at the physical MGA meeting. Bye-bye.
So much. Okay. Next speaker would be Dr. Bison. Under the name of the library, lecturer on Point University. Yeah. And his topic would be demonstration experiment of marine plastic waste monitoring. Okay, Bison, the floor is yours.
Okay, thank you very much, Professor Shibasaki, and greet everybody at Phuket. Sorry, our team could not be with you at Phuket. So our talk is demonstration experiment of marine plastic waste monitoring system. We are a group of 4 researchers. We team up from Japan and Thailand. So I'm Paisan Santithamnon will talk on behalf of Mr. Nagao and Dr. Honsawa and I myself, we are from Chulalongkorn University. Another researcher is Dr. Virod from Burapha Universities. Okay, rationale. So the reason for this project is that I think most of us be aware that the problem of environmentals in ocean area, lots of tons of plastic waste exist in the world oceans, and we would like to study the outflow in the area of Gulf of Thailand, and we know that about 30% of this discharge of these marine debris coming from Southeast Asian country. So we start with a small part of Southeast marine area in Southeast Asia. This is the Thai Gulf. So, and at the ASEAN Summit held in Thailand in June 2019, we have the Bangkok declarations that we would like to cooperate to reduce the marine plastic waste. So the purpose of our research projects is that we would like to understand the inflow route drifting of those marine plastic waste in the upper Gulf of Thailand. And this research, we will develop a system for plastic waste monitoring, starting from about 20 GPS probes within the upper Gulf of Thailand. So the key innovation of this research project, beyond we using the GNSS device to tracking the positions of those marine plastic waste, we will use the IoT technologies and also a low power wide area network. We will set up here in the Upper Gulf of Thailand. And then we hope that we will gathering the monitoring data, the outflow, the route of those plastic waste in the Gulf of Thailand. Once we got quite a big number of data, we hope that we could make analysis, and together with other source of the remote sensing data, we might make some AI analysis at the end of this project. So the configurations of these projects, the key device will be, of course, will be the GNSS receiver. The communication will be the LPWA, that is the low power wide area network. The system might, we might put some solar power battery, but I think for a short period of time, for 1 or 2 years, we might, a big battery would be enough for the purpose. And the communication antenna. So we should provide 2 gateways within the Gulf of Upper Gulf of Thailand to get it to receive data from those GPS probe, and then we'll develop a monitoring system. So this is the schematic of our research projects. The GNSS probe and battery, everything we put in the bottle. We plan to make about 20 pieces of this, put in the oceans, or sometimes if we could find some plastic debris in a big amount, then we might put on those plastic debris. And then the data will coming through the gateways. We're using the LP-WAN, that will be the LoRa. About the frequency will be about 900 megahertz. All the data will coming through the network of pass through the gateways, and then we could retrieve the data to the 3G or 4G network, and then we put everything in database, and then we show up on the monitoring system. So this is the idea, how can we make the GPS probe with the LPWA network. So this is the system that we use this from Sony. So we see the receiver on the picture below here, side B, this is the receiver. And on the other side is the ceramic pad, GNSS antenna. It's a low power. On the right side, you will see the plastic bottle, the PET bottle. We hope that we could seal its protect from waters. And then you will see in the green piece here is the LoRaWAN antenna. So we plan to make 20 pieces of this. The battery we put inside is quite big, so we believe that it will last about almost 2 years. That will be enough for the projects. 2 gateway will be provided by Sony corporations from Japan. It's a so-called Sony Ultratech system. It's a LoRaWAN system with frequency of 920 megahertz antenna. And at the back end, we can get the data through the 3G networks. IoT tracking is coming. One of our recent projects at Chulalongkorn University, we also experiment with such kind of the IoT tracking device. You see on the right picture here. It's even powered by solar energies. Interesting is that the communications by this GPS tracking device is NB-IoT. That is another kind of low bandwidth communications. The most interesting feature of this system is that the airtime for the communication between GPS probe and the gateway is quite cheap. For this system, we use it for relief good distributions for disaster management of the Thai Red Cross. That means we have temporarily about 100 pieces of this, almost 100 pieces of this, to put in any trucks during when the Thai Red Cross would like to distribute the relief goods. But you know, as this truck, they don't need a higher data rate, like might be taxi tracking, you might need a 1 seconds data rate. But this kind of tracking, we just would like to know every 15 seconds or 1 minute, where are those goods is going. So we can achieve this by using low bandwidth data like NBOT or LoRa. And in Thailand, if in case of on land or inland, we pay only about $10 per year for the communications. So this could be very cheap, but of course, the pro is cheap, but the con is data rate you have to reduce. So this is the example that we have done with the system of the Thai Red Cross service of Thai Red Cross Society, supporting the relief good transportations. So we don't need, as I told you, we don't need a high data rate. Only every half a minute we need the position of the car or transporter. So similar system, we use NBOT network here, and then from the NBOT GPS tracking device, about 80 units can remit the data to the server, and then the server can show up the relief team of Thai Red Cross to take a look or follow up the transportations of relief goods. So let's back to our current projects of tracking of the marine debris. We plan to put 2 gateways for the LoRa. That means we will use private LoRa gateways. One we will put one tower at Samut Prakan, and the other one we hope to put on the top of a quite high hill of Pattaya cities. And the coverage of the design will about 50 kilometers, which to gateway we hope that we will cover about almost 50% of the upper Gulf of Thailand. So beyond that GNSS tracking technology, we also use the other remote sensing technique, since we know that every 6 to 12 days we could have remote sensing data from multi-spectral satellite, especially Sentinel-2 or even Landsat 8 or the new coming Landsat 9. So for the ocean debris, we could perhaps use the FDI floating debris index, or we could analyze the plastic index, or simple NDVI, normalized different vegetation index. So we hope that if we don't have the trouble with cloud, so we might get this kind of index and make analysis together with the GNSS tracking data. So in Thailand, even we don't have quite often a very big floating plastic debris in quite a big group, but sometimes in some case, like in 2017, it happened that we have a large patch of garbage size up to 1 kilometer, for example. But if we could not find a big patch like this, because big patch like this we might find mostly in the big oceans, that means outer part of Gulf of Thailand. So we might find some plastic bottle of a raft, sometimes because of the fishery is a kind of fishery gear in Thailand. So we might put some of this bottle or some of this GPS probe on those raft during our research. So the aspect of our result that in this project, we hope that we will get the big pictures, some pictures at least in the upper Gulf of Thailand, how do this plastic waste is drifting. And we hope that in the same scheme, we might expand further to the South China Sea ocean in cooperation with others countries like Malaysia and Indonesia in the futures. And we hope that this research will be attract attention to others, our local government and our central government to mitigate the problem of the plastic marine debris in the futures. And we could visualizing and quantifying the actual conditions of marine debris by using our web-based system that we can easily deliver the data to the audience. So thank you very much. And if you any question, I think our team is in this Zoom, so please do it. Thank you.
Thank you very much. Very interesting presentations, Dr. Pasa. Do you hear me?
Yes, yes, I hear you, Professor Shibasaki. Yes, please.
I'm very glad that you see that the very kind of integrated and a comprehensive approach for such a very important social issues. And the question I have is probably some of the coastal engineering researchers, I mean the simulation of the drifting, actually the object on the sea surface. Anyway, I just wonder whether the integration with simulation or the researchers with the capability of developing simulation models might be quite helpful for the longer term development. Anyway, I appreciate your comments.
Okay, thank you very much, Professor Shibasaki, for your suggestion. That is indeed very interesting. As you know, actually, like for example, GISDA also have the coastal radar, which monitoring the ocean's current. That we have, our group also have interest to join with GISDA, and we will discuss how to collaborate with such other ocean engineering data. Thank you very much.
Yes, you hear me now.
I can hear you. I can hear you.
Some of the microphone system issues. I'm here to join.
Okay.
Yep. Okay. Anyway, thank you very much for your talk.
Thank you very much.
Okay. So may I actually invite the next speaker? Next speaker is Shiraj. Sorry. The title is Automatic RTK Madoka and RTK Shira switch receivers. And Mr. Mohammed Shirati Ami, Core Corporation. Are you ready for your presentation?
Yes, Dr. Shibasaki, thank you very much. So I'm very sorry for the confusion earlier. So can you hear my voice? Hello?
Yes, we can hear you. We can hear you.
Okay, so also you can see the slides.
Yes, the slide is okay. We can see the slide.
Okay, thank you very much. Okay, so I will start my presentation. Is it okay to start? Okay, so I will start my presentation. So my name is Mohammed Shujai Amin. So I work for Core Corporation, and today the topic of my presentation is automatic RTK Madoka and RTK CLAS switch receiver. So firstly, I would like to thank the MGA team and all the organizers of MGA, the presenters, and also the system providers for their support. So thank you very much. And I would talk about firstly about my company, and then about the services of Madoka, CLAS, and RTK. And then we would like to talk about the RTK Madoka and RTK CLAS switching function. And then I will demonstrate the results of that technique. So about my company Core Corporation. So it was established back in 1969, and back in 2005 we entered in the satellite business, GPS business, and in 2013 we released our sub-meter accuracy receiver, and in 2018 we released our centimeter level centimeter accurate GNSS receiver. So now we are working on receivers, and we are improving our services and our products. So we are located here in GNSS Solution Business Center in Kurokawa, Kanagawa, Japan. And we are working in GNSS based products and projects in this center. So for Code Group, our main business is GNSS, IoT, cloud, vehicle systems, and embedded systems. So we are working in these domains. And next, I would like to come to my topic of presentation, which is the switching between RTK Madoka and RTK CLS. So for RTK positioning, as we know that rover and base is required, and there should be some kind of communication between the rover and base to get the corrections. And for Madoka PPP, we know that SSR messages, orbit and clock corrections are sent via L6 signal of QGSS satellites. And if the receiver can decode this signal, we can get the precise positioning or centimeter level positioning with no communication medium in between, for example, any network medium, etc. And this service is available in Asia. For CLS, we know that the CLS signal, L6T signal by QGSS satellite, is providing the corrections of CLS of PPP RTK, and it is available in Japan. And for the receiver supporting CLS, we can get the precise positioning or centimeter level positioning without any network on any communication medium. So here I would like to compare the precise positioning services. So for CLS, we know that it is available in Japan, and the convergence time or time to first fix is up to 60 seconds. And the accuracy is horizontal, and vertical is up to 2 centimeter to 6 centimeter. And we see that GPS, Galileo, and QGSS, we get the corrections for these satellites, and this service is free. For Madoka PPP, we know that it is available in Asia, and the accuracy is up to for static positioning, it is up to 3 centimeter horizontal with respect to 6 centimeter vertical, as measured by the core RTK receivers. And for kinematic, the accuracy is a bit more. And the convergence time for Madoka, if we measure by core receivers, so it is up to 30 minutes. And we can get the corrections of GPS, GLONASS, and QGSS. And this service is also free and available in Asia and Oceania region. So if we talk about the network RTK, so in Japan, we have network RTK services, as we also see the Jimili service today in the presentation. And the communication range of these services is the range of the mobile phone. And the accuracy of this service is very good, and convergence time is very good. And we can get the corrections of absolutely all the GNSS satellites, but this service is paired service. So our proposed idea is to get the merits and demerits of every service and use these services in a case that we can get centimeter level positioning in all cases or all kind of environments. So next I would like to talk about our GNSS receiver, which is recently released, the Cohack Infinity 10. So this is QGSS CLAS supported small receiver up to 100 grams in weight, and the dimensions are equal to a single business card. And it is we can get the performance at low price but equivalent to first-class GNSS instrument. And this receiver is ideal for incorporation in equipment and high performance, lightweight, small in size, and low cost. So next I would come to my topic again, and I would like to talk about the merits of switching. So why we presented this idea, or why we are working on this idea of switching the services. So we categorize the services in two modes. One is the accuracy priority mode. So in this mode, our main focus will be to get the accuracy, and one is communication cost priority mode. So as we know that in Japan, for network communication, we have to pay a big amount, and also in Asia also we have to pay some amount for it. So we prioritize our receivers in these two modes. One is accuracy priority and second is communication priority. So in RTK CLAS switching, for example, if we are in Japan, the accuracy priority mode, we will prioritize the use of RTK technique for getting centimeter level accuracy. But in cases when we face problems in communication or any other problems, then we will switch to CLAS mode. And similarly also, in the communication cost priority mode, we will prioritize the CLAS service, but in case we receive the problems in QZSS L6 message, for example, if there is problem in decoding or the alert message of the L6 signal is on, then we'll switch to the RTK mode. So for long operation, we prefer the communication cost priority mode, and for other operations, we prefer the accuracy priority mode. And similarly for RTK Madoka, we will use the similar techniques. So by mutually compensating these services, we will try to provide you centimeter level accuracy in all conditions by switching them automatically. So let's talk about the method of switching. So firstly, for example, we have in RTK conditions, all the conditions of RTK are met. For example, the communication is available, the baseline is on the threshold, and we are receiving the base observations, then we will go for RTK. And the CLAS or Madoka conditions, for example, if we are receiving the QZSS L6 message continuously and the alert message of QZSS L6 is off, then we will go for the CLAS conditions. So if any of the conditions are not met for these RTK and CLAS or Madoka, then we will switch the service. So the first, as I talked previously, RTK priority mode and CLAS or Madoka priority mode. So we will switch contrarily based on the conditions. So this is the configuration or the model of the GNSS receiver, which we are in phase of testing, and it has configuration for RTK and Madoka. So for example, from the GNSS engine, we continuously receive the Madoka messages, and we compute the anemia using the Madoka mode. So we get the status information from the receiver or GNSS engine. So if any of the information which we get from the status information shows that we have any problem in RTK or in CLAS or in Madoka, then we switch the service. So the most important thing to tell is that the Madoka positioning in this configuration will always be turned on. We deliberately did this so that we can reduce the convergence time of Madoka. For example, in case when we switch from RTK to Madoka, then the Madoka receiver is already converged in that time. So we also are in progress of applying for the patent for this, and that's all. So now I would like to demonstrate the test results of RTK and Madoka switching. So these are the switching of RTK and Madoka manually. For example, we are not doing this automatically. We turn on the receiver in RTK mode, and after some time, we change the configuration of the receiver, and we switch it to the Madoka mode. So in this case, we see that the receiver takes time to converge, and this time is about more than 20 minutes. And then we get the positioning, which is converged positioning or centimeter level accurate positioning. So this result shows the manual switching of RTK to Madoka. So next, I will talk about the core receiver, which will switch the Madoka automatically. So in this receiver, we turn on the receiver with RTK mode, and after some time, we switch the receiver to Madoka mode. So we see that after switching, the convergence time is reduced to 0 seconds, and we are getting the converged or centimeter level accurate positioning. And this is the static positioning results for manual switching and automatic switching of the receivers. So in manual switching, we see that it took us about 15 to 20 minutes to converge to centimeter level positioning, and the accuracy of Madoka is not as good as automatic switching, because in this time we have to converge in Madoka. And next is the kinematic test. In this test, we perform this test on the rooftop of our R&D center, and we demonstrated it as a rail. And in this method, in this test, we switched off the network connection to convert the mode to RTK mode to convert the mode to Madoka mode from RTK mode. So as I told that in case when the network is switched off, then receiver will convert to Madoka mode automatically. So sorry. So these are the results of switching to using automatic switching and manual switching in kinematic mode. So we see that the blue line indicates the RTK, the orange is Madoka, and the gray is the orange is the Madoka, and switched Madoka when we switch from RTK to Madoka, and the gray is Madoka only receiver. So we see that the positioning is absolutely similar in all these conditions, demonstrating that the operation was performed successfully. And here we see the results on the plot, and we see that for Madoka and after switching RTK to Madoka, we get the accuracy almost similar, showing the operation was performed successfully. So the summary of my presentation is that we analyzed that we can by focusing on the merits of every service, we can get the centimeter level positioning in all conditions, and we switch the RTK to Madoka and reduce the convergence time of Madoka to approximately 0 second. And by reducing the convergence time, we also increased the accuracy of the receiver. And also in the kinematic results, we see that the proposed solution was giving us good results. And this is a solution for the all conditions. For example, in case of autonomous vehicles or any other conditions, when we are looking for the backup services, then this is the receiver which we will propose to our customers. That's all. And at the end, I would like to exhibit our receivers, Cohack Infinity 10 and Chronosphere L6 QZ Neo. So this is CLS supported small GNSS receiver. So this is CLAS and Madoka supported receiver. And this is the Michibiki L1S disaster support supported receiver. So that's all for my presentation. Thank you very much.
Thank you very much for your presentations. The result is very impressive, and that it should be very useful. And actually, on this session room, Dr. Kogure is here, so may I invite him to make any questions or whatever? Probably you may need to use this microphone, if possible.
Thank you very much, Shimataki Sensei. Dr. Yami, so I'm Satoshi Kogure. So I worked for the cabinet office until the end of August. And now we are working for JAXA. And I am a director of development of Madoka in JAXA. So I appreciate for your effort to utilize Madoka and Shiras switching depending on the environment. So I had a similar idea. So yeah, but in the world, so there are rural area and an urban area where infrastructure is very enough distributed or not. So this kind of approach is a very good idea. So I have one question. So unfortunately, so I missed core of your presentation. So what is the most difficult point? Judging switching the Shiras and Madoka or PK. So please provide your thought on this issue.
Okay, thank you very much, Dr. Kogure. So for switching, actually, if we see from RTK to Madoka, then the most important thing is network issues. For example, we are in mountains or any place near where we are facing the network issues, then we will switch. And also in urban area, you see that we have in CLAS, we have limited number of satellites available in urban canyon, for example, huge buildings. And the elevation of satellites is not high enough to get the centimeter level positioning, because we are not converged to centimeter level positioning. So in all these conditions, we are monitoring continuously all these conditions and performing different experiments. And we will update this switching method continuously based on our research, and our group is working on it. Yeah, thank you very much. So do you have any other question?
Thank you very much. And Mr. Yami, actually, you have had another question. That question is, let's say, that this Madoka receiver product was already in the market.
Oh, okay. So, so this is this product
signals or systems.
Oh, okay. So this product, so this is our next release of Core Corporation, I guess so. Yes. Okay. Yeah. So this is our next release. So we are in phase of development of this product. So soon we will announce this product in market. Yeah. Thank you very much.
Very much for a very interesting talk. Okay, so then I would like to move to the final presentation. And the final presentation would be by Mr. Victor Koo, Singapore Land Authority, and his talk is precise GNSS positioning. Mr. Victor, do you hear me?
Yes, I can hear you. Good day, everyone. You can hear me?
Your talk.
Let me share my slides. Just want to confirm you can see my slides.
Yes. Yes.
Okay, so I will start my presentation now. Thank you for inviting me to share what we are doing in Singapore. So today I'm going to talk about the infrastructure and the services of precise GNSS in Singapore, as well as the industry application. You know, how does industry use this application, particularly to support the Smart Nations initiative in Singapore. So I am Victor Koo. I work in the Singapore Land Authority, and in Singapore Land Authority, we focus on survey, mapping, positioning, as well as geospatial related activities. Right? So GNSS, I think this is an important infrastructure. There are more than 100 satellites that we can use for in positioning as well as in other applications. So today, GNSS is a utility, that would be used for sustainable development. So there are many applications of GNSS, ranging from surveying, mapping, aviation, transportation, and many new applications like drones, constructions, and so on and so forth. So the usage of GNSS can largely be divided into location-based services, agricultural, surveying, rail, road, maritime, and aviation in general. And precise GNSS is important because this is where a lot of applications are depending on. Also, in this case, precise GNSS, we are looking at a few techniques, the RTK techniques, which is quite common, the network RTK technique, the SBAS technique, and the new one, which is the PPP and also PPP RTK techniques. And these are the techniques that are able to provide real-time sub-meter to centimeter accuracy by having an infrastructure on the ground to provide augmented message to the user in real time. Right? So in Singapore, we operate, so SLA operate an infrastructure known as the Singapore Satellite Positioning Reference Network Infrastructure that will support precise GNSS services in Singapore. There are 8 stations around in Singapore because Singapore is quite small, so 8 stations is enough to cover the whole of Singapore. And this is the infrastructure that provide GNSS RTK at centimeter level whole of Singapore. Besides that, it also provide the code-based differential GNSS as well as post-process on-demand services to our user. So it is important that the services that we provide to our user is transparent to the user. So, in order to be able to promote the wide usage or wide application, especially in new areas. So we have our own web portal with a lot of information that supports the user. We have proper authentication for users, so users can easily sign up to be a user of the system, through a proper business model. And we also promise a certain service level for our user who paid for the services. So the web portal is one area to disseminate the information, and also for user to be able to access the data. We also provide a mobile application to our user. That is for us to alert the user if there's any issue with the reference station, as well as some simple application for the user to choose their reference station. In terms of single base RTK, they are able to use the app to determine which is the closest reference station for the user. So these are important applications between the reference station network that we provide to our user to promote, and also to make sure that the user is able to use this in a transparent manner. So in Singapore, because of our push for smart city, there is a greater need for accuracy in terms of positioning. That's the reason why the infrastructure has become increasingly become more important. We have many users from the different sectors. Public service, which is in the government, we have a lot of users. We also work with a lot of technology and solution integrator to provide additional services, the research and academics, construction and surveying sector. I would go on and talk a bit about autonomous technology. These are the new sector of user and many other things. So generally, we divide our precise GNSS user into three major groups. The positioning group, these are the group that covers the area of surveying and mapping, engineering work. The navigation group, which is more on transportation and more on in a kinematic manner, and the monitoring group, which is more for monitoring purposes. So the first group, which is a traditional application, this is quite common in surveying, in mapping. This precise GNSS services is being used extensively in Singapore. In fact, most of the boundary survey are carried out using GNSS or precise GNSS as the control for the survey. And our periodic national mapping campaign, be it area mapping or ground-based mapping, the precise GNSS services is key to support this kind of data collection. So from the perspective of mobile mapping, so we run extensive laser scanning around Singapore on a vehicle, and RTK and precise GNSS is a key technology for positioning in this data capturing. On top of that, there are many other applications on the road, on a vehicle, to detect pavement distress using laser crack measurement systems. We have systems that are running on the road that is trying to scan the underground using rapid ground penetration radar. These are the systems that is in mobile situation, and a precise RTK is required in this application. The other major application that is currently being tested is this development of autonomous vehicle. So in this case, we are looking at passenger autonomous vehicle, either a private passenger vehicle that's being developed that would need a RTK, a very precise positioning for the localization, as well as big buses and also transportation port that has been developed in Singapore, and some of them has been in operation in an autonomous manner. On top of that, there are also many developments around the area of autonomous mobile robots. In Singapore, many of these robots are developed because of we are lack of human resource, we need higher productivity. So a lot of applications like in the cleaning sector, in the grass cutting sector, as well is in security sectors. These robots are developed that would work autonomously, and they depend on RTK as the primary positioning tools, for the localization. One example very extensively is this grass cutting monitoring system. A company in Singapore, a startup company, developed low cost RTK boxes that can be used on any grass cutting equipment as well as on a grass cutting person, and this will help to monitor the progress of grass cutting as well as the progress of the grass cutting in real time. So this is a very good application for smart city. Besides that, in construction, there's a lot of development as well from the robotic perspective that utilize a precise GNSS, smart crane application, piling application, as well as road paving application are using the surveys that provide by SLA. And also, I think in terms of the publicity, in terms of the promotion, I think it's very good for us to be able to publicize what has been done, what has been developed in the industry, so that more adoptions can be, we want to promote more adoption of this precise GNSS. In the area of drones, as well, it is a very important application, especially for autonomous drone. RTK is a key technology that would allow a precise landing and precise flying path. The last application that I would like to share is the aircraft landing system. So in Singapore, we have started to look into developing of a ground-based augmentation system that would based on precise GNSS, especially for a special airport that is quite close to our neighbor. So this is another application that is key for us to move into smart city. With that, I'll end my presentation here, and I'll welcome any questions. Thank you, everyone.
Yes. Oh, sorry. Yeah. Do you hear me?
Yeah, Professor Pataki, I can hear you.
Yeah, thank you very much for your presentations. I know that the silent is a kind of, let's say, long history for the establishment. And also, I very like to see a lot of new applications ranging from the very precise positioning, kind of traditional ones, to the more advanced autonomous controlling systems. And but at the same time, Mr. Ku, what would be a kind of challenge for the next development of this silent? It seems to me the silent itself is almost established, but probably you may envision another challenge for the future or next generation silent. Anyway, I appreciate your thoughts.
Yes, thank you for the question. Yeah, in fact, we believe that this is just a beginning of our journey. There is a lot of improvement that we can work on with our system, the precise GNSS service in Singapore. I think first of all, a good business plan is important. So we have a business plan, and we think that this business plan is still not good enough that would be able to support very advanced application. This business plan today that we have is good for traditional application, and currently is still not very good to support autonomous vehicle applications. So that's number one. We are putting effort in the team to come up with some way of charging our user fairly and effectively, so that the application can be used by more users, can be shared, because there is a cost for running the application or running the infrastructure. So we need to have an equitable business model that the different application can benefit from the infrastructure. This is a very challenging task. The reason is because there is really no established model that we can follow. It also ranging, the differences also ranging from one city to another city. We have a very small market in Singapore, and it's very hard for us to find a balancing pricing system that would meet the traditional application as well as the new application. So there's one area. I think technically there are also areas that we need to improve. I think the availability of the systems 24/7 that would support autonomous vehicle. I think traditional application, even though it's it's 24/7, but we are allowed more time, more downtime. But for the application of autonomous vehicle, it is very critical, and we have to find ways of really making sure that our system is running 24/7. And also many other technical questions. So currently, what we are interested in is that working with the industry partner to understand the need, especially from the autonomous vehicle application perspective. We wanted to identify the need for when the autonomous vehicle is in full operation. In today's context, most of our autonomous vehicle are running in a pilot mode or in a mode of demonstration. When it is in full operation, what is the gap of this system? I think that's a question that we keep on asking ourselves, and we would like to know what's the answer. And so that we can prepare ourselves, we can improve the infrastructure to support our future application. Back to you, Professor.
Oh, sorry. Okay. Yeah. Thank you so much. And any other questions from this session room? No. Okay. So if not, I would like to conclude the session today, and also I really thank all the speakers for the very excellent and also the very informative presentations. Okay, yeah, thank you very much. And at the same time, I would like to apologize for some sort of the troubles and also the confusions. And at the beginning of the session, we have had a really unfortunate kind of issues, but after that, the staff here had very best efforts to recover such sort of the audio system issues. So anyway, finally, we could finish successfully the sessions today. Okay, anyway, thank you very much for your participation and also the contribution. Thank you very much.